Hi, welcome to Differential Equations, Lesson 1.1, Part 1. This is the demo for the lesson. So, what is a differential equation? It's an equation that includes one or more derivatives. A solution to a differential equation is a function that makes the equation true. So that's what makes differential equations very different from the equations that you've solved in the past. It includes derivatives, and its solution, rather than being a number, is a function. So for example, what function or functions makes the following differential equation true? dy dt equals sine of t plus 2. So the solution is a function that makes this equation true. So my solution would be y of t is a function whose derivative equals sine of t plus 2. So what function has sine as its derivative? That would be negative cosine. Function that has 2 as its derivative would be 2t. And then we can always add a constant because its derivative would be 0. So there's a whole family of functions that satisfy the equation above, whose derivative would be sine of t plus 2. So the general solution is this. Negative cosine t plus 2t plus c. To obtain a unique solution, like one single solution, you would need an initial value for the function. So for example, same differential equation, dy dt equals sine of t plus 2, but we want to find the particular solution that satisfies y of 3 equals 5. So I know the general solution is this, and I want y of 3, which in this case would be negative cosine of 3 plus 2 times 3 plus c. I want that to equal 5. So then I can just solve for c. So that means that c would be cosine of 3 minus 6. It's very, very tempting to circle that and call that the answer, but that is just the c value that's a piece of the answer. The particular solution is a function. Okay, it's y of t equals negative cosine t plus 2t, and then replace the c from the general solution with the particular value we just found. Cosine of 3 plus 6. So that function has as its derivative sine of t plus 2, and if you plug a 3 in for t, you get 5. Okay, so finding solutions to differential equations can be very difficult. The one we just did was pretty straightforward, but it can be very difficult. So one thing that we can do is you can always check if a function is a solution to a differential equation. Makes it much easier than just finding a solution. If you're given a potential solution, you can check. Okay, so to show a function is a solution, we have to show that if we replace every y in this equation with this y, that we get a true statement. So I'm going to start by copying this equation down. So I have 4t squared y double prime plus 12t y prime plus 3y. I want to say, does that equal 0 for the y I'm given? So the y value I'm given is t to the negative 3 halves. So where I have a plain y, I can replace it with t to the negative 3 halves. But I also have a y prime and a y double prime. So I'm just going to do a little aside here. And if y is t to the negative 3 halves, then y prime is negative 3 halves t to the negative 5 halves, and y double prime is 15/4 t to the negative 7 halves. And now I'm going to replace y double prime with this, y prime with this, and y with this, and see if this equation is true. Okay, so I have 4t squared times y double prime, which is 15/4 t to the negative 7/2, plus 12t times y prime, which is negative 3/2 t to the negative 5/2, plus 3 times y, and y is t to the negative 3/2. Does that equal 0 when you simplify the left-hand side? So now I'm just going to do a little arithmetic. I've run out of room. This always happens. Okay, so I'm just going to jump to a new slide and finish this. Differential equation down. I replaced all the y's, y primes, and y double primes with expressions from the given potential solution, and then showed that the equation is in fact true for that function, which means that function, t to the negative 3/2, is a solution. Okay, so next topic is the process of describing a physical situation with a differential equation is called modeling. We'll be looking at modeling several times throughout this class, but the general steps are: state your underlying assumptions, identify any relevant variables or parameters, and use the assumptions in step 1 to formulate equations that relate the variables in step 2. Okay, so here my 4's cancel, and I end up with 15 times t to the, now I'm multiplying like bases, so I'm going to add the exponents. So add 2 to negative 7/2. Negative 7/2 is 3.5. Negative 3.5 plus 2 would be negative 1.5, or negative 3/2. Plus, okay, so 12 and the 2 in the denominator, that would give me 6. So I have negative 18 t to the, I have t to the first times t to the negative 5/2. You're going to add the exponents, and you get negative 3/2. Plus 3t to the negative 3/2. Does that equal 0? Well, now they are all like terms. So I have 15 minus 18 plus 3. That is 0t to the negative 3/2. Does that equal 0? Yes, because 0 times anything equals 0. So t to the negative 3/2 is in fact a solution to this differential equation. Okay, so I copy. So we're going to apply this process to looking at the U.S. population. So I have some data points for the U.S. population from 1800 to 2000. The first model we're going to look at is called the Maltusian Model. And the Maltusian Model is a model that has a special assumption. So the assumption is that the growth rate of a population is proportional to the size of the population. So as the size of the population gets bigger, the speed at which the population grows gets faster. So that is an assumption that makes sense, because the more people there are in a population, the more frequently they encounter each other, and the more quickly they are able to reproduce. So our variables here are the size of the population. So let's let that be P. P equals number of people in U.S. population. And then we've got T for time. We'll say years since 1800. And then we've got the size of the population, check. Proportional, whenever we have something proportional, we have a constant of proportionality. So let's call that K. Of proportionality. And then growth rate of the population, that is the derivative of the population size. That would be dp dt. So I'll just jot that down. dp dt equals growth rate of the population. So the Maltusian model is where we just take this sentence and translate it into symbols using the variables that we identified. Okay, so the Maltusian model, it says that the growth rate of the population, which is dp dt, equals proportional to the size of the population. So that means a constant times the size of the population. dp dt equals k times p. So this differential equation, the Maltusian model for population growth, it's called a first-order differential equation because it contains only first derivatives. If you had second derivatives in there, it would be called second order. And it's called an ordinary differential equation because it does not contain any partial derivatives, which you probably learned about in Calc 3. So in this class, we'll deal only with ordinary differential equations, or ODEs for short. So we'll have no partial derivatives. So we want to confirm that P of t equals 0 is a solution to the Maltusian model. So that means that if the population is 0, we satisfy the Maltusian model. Okay, so this special type of solution is an equilibrium solution. It's called an equilibrium solution because it's constant. Everything is in equilibrium. The size of the population is constant. It's never changing. It's always 0. So equilibrium, not changing. Okay, so to confirm that it's a solution, we need to plug in like we did in our earlier example. So I start by copying down dp dt equals k times p, and then my potential solution is P of t equals 0. Okay. And I need also dp dt to plug in, and the derivative of 0 is 0. So if I plug in for dp dt, I'm going to put a 0, and for p, I'm going to put a 0. So I get 0. Does that equal k times 0? And yes, it does. 0 equals 0. So we have confirmed P of t equals 0 is in fact a solution.